Let's solve this trigonometric equation involving cosine function. This equation, do you realize this is a quadratic form? Quadratic, if we view the cosine x as a variable, let's just simply replace the cosine x with a simple letter u. So then cosine square will become u square. So here is what we want to do. We just simply replace cosine x with a single letter u. So you realize that is a variable, right? We call it u, and then your equation becomes equation of u, and we see that's a quadratic equation of u. So that means this equation is a quadratic equation of cosine x, right? If we treat cosine x as a single variable u, then we see the quadratic form immediately. So then solve this equation is not new. You just try to factor if possible, for example, or you can use quadratic formula. So let's factor it. So it is 2u. If we 2u, for example, once we factor, so because this u can be factored, right, as this, and this one you can put here, and the -1 product will result in a +1. So then you can see the cross multiply will be 2u will become a -2u minus u -3u. So it's possible to factor as 2u minus 1, u minus 1. So let's 2u minus 1 times u minus 1. After we factor it, then we know by the zero factor property, then either 2u minus 1 is 0 or the other factor, u minus 1 is 0. Then we can solve. So the first equation means u has to be half because 2u is 1, so u is half. The second equation means u is 1. So u is either half or 1. And that means we have found cosine x. Cosine x is either half or 1. But that's not it, because we have to find x. So far, we have found cosine x. So then we want to find x over this interval from 0 to 2 pi. So you see the process is recognize the quadratic form, right? As soon as we replace cosine x with a u, then you recognize the quadratic form and you factor it. Because the product is 0, then either factor, one of the factors must be 0. So either the first one is 0 or the second factor is 0. So we can find values of u. So u is 1 or half. That means cosine x is 1 or half. Then how do we solve from here? We're not done because we have to find x. So if cosine x is 1, what is x? The x will be, so let's solve first one. Cosine x is 1, and over that interval, and we know it's decreasing and then increase to 1, so that the only x solution on this interval is 0 when x is 0, right? So we're trying to find what x over this interval from 0 to 2 pi. such that cosine x is 1. So the only solution is 0. Now, how about the other equation? Because cosine x could be half. So if cosine x is half, what should be x? Still over the interval from 0 to 2 pi. So if you want to write the inverse, suppose you write x as inverse cosine at half, then this x is only from 0 to from 0 to pi. Remember, the range of a cosine inverse is only from 0 to pi. So we can write so anywhere from 0 to pi, right? What is the x? So this way you find an x in that by doing inverse. So, but still, we can give such a cosine inverse. Cosine inverse that means what is the angle x in the interval from 0 to pi whose cosine is half. And we know that value is pi over 3. Yeah, pi over 3. But we want to find all the x's. That is, in order to find all the x's over the interval from 0 to 2 pi, so we need to find out, is there another x, another solution? So the solution, if we have found 1 in the first quadrant, we know the cosine value can also be positive and at the same value in the fourth quadrant. So the fourth quadrant, the angle 2 pi minus pi over 3, that which is 2 pi, you know, it's 6 pi over 3, right? Minus pi over 3, which is 5 pi over 3. So this angle has a reference angle is pi over 3. But these two angles will have the same cosine value. That means half. So we just have found over the interval from pi to 2 pi, because we found 1, but there's another one from pi to 2 pi. And in that range, we know in the fourth quadrant, this angle has a reference angle, which is pi over 3. And both this 5 pi over 3 and pi over 3, they have the same cosine value. And the cosine value is half. So we have found 2 solutions for the second equation. So right now, we only consider the interval, right, from 0 to 2 pi, found 2 solutions for the second equation, which is pi over 3 and 5 pi over 3. And for the first equation, we have found x equals 0. That is a solution in that interval. So let's summarize our solution set for the equation. So once we have found the cosine value is either 1 or half, then when it's 1, we have a solution over the interval. Once it's a half, when cosine x is half, we have found 2 solutions over this interval. Therefore, the total number of solutions is 3. We have 3 solutions. So 0, pi over 3, 5 pi over 3. So all the 3 are possible solutions. So we call it solution set. So this is the set of all solutions from that interval. So next question is, can we find all solutions? That is, can we find all solutions over the interval from negative infinity to positive infinity? So that means solutions on this interval, we will have more solutions, because from 0, we can find all we can add 2 pi, right? Complete rotation, for example, an integer multiple of 2 pi can be added to 0, then they still are solutions. Because if at 0, cosine 0 is 1, then cosine at any of these will also be 1, because the cosine is a periodic function with a period 2 pi. So we can list all solutions from this one solution. Then on this interval, we can find all solutions. And then if you have pi over 3, and then pi over 3, you add, also you see this integer multiple of 2 pi can be added to pi over 3, then you can find all solutions over the interval from negative infinity to positive infinity. And again, for 5 pi over 3, if we add integer multiple of 2 pi, that we can find all the solutions over the interval. So, of course, all these solutions, including those pi over 3 and 5 pi over 3, right? As long as n is 0, you see, including that special solution as well. So that means, yeah. So that's the set of all solutions. Yeah, we certainly, when we give the solution set for the part B, and we made use of the period of cosine function, because 2 pi is the period of the cosine function. So if you add any integer multiple of 2 pi, then you still result in the same cosine value. So that's why we write, as soon as you find one solution, you can represent all solutions using the fact that cosine function has a period 2 pi. So for this problem, I want to summarize. You see, the step 1 is to recognize the quadratic form, solve a quadratic equation. Once you solve a quadratic equation, you find x, cosine x. Yeah, so this is a quadratic equation in terms of cosine x. As long as you find that, then you can solve for x. Once you know the cosine x is a certain number, for example, 1 or half, and then you can go from there to find x. So 2 steps. And also, depending on where you found, you try to find x. If you over the smaller interval, then you maybe you have finite number of solutions. Over this interval, from negative infinity to positive infinity, due to the periodic nature of cosine x, you can find infinitely many solutions. So let's look at another problem. So here is another problem. This equation involves both sine and tangent. Okay, it's not a quadratic form, but still we can try to see that sine x is a common factor, right? We can factor it out. Once you factor sine x, you get tangent x minus square root of 3. So this equation has the sine x as a common factor in both terms. So we factor out the sine x, then you can write the left-hand side into a product form. You see the product form. So once you have a product, because the product of these two is 0, then we can apply the zero factor property. So then one of the two factors must be 0. Okay, let's go ahead and see if the product is 0, then either the first factor is 0 or the other factor is 0. So then we can solve from the sine x being 0, we can get the one equation, right? From tangent x minus square root of 3 is 0, you can find another equation. So now this way we can try to solve each equation to get x. So we go from there. Once we get sine x or tangent x, then we go from there. So let's think of the sine x. If the sine x is 0, if sine x is 0, okay, this is the one I solve first. And then what is x? First, I solve for part A. I only want to find the x from that interval whose sine value is 0. So, and we know immediately x is a 0 or pi. And if you just recall the sine curve, right? If you have x, you have a sine x, you can draw the sine x from 0 to 2 pi. And you can see that when x is 0, when x is pi, and we have two solutions. Yeah, 0 and pi at these two places, sine x will be 0. Yeah, we have found two solutions over this interval. And then let's continue to find, so we just solved the first equation, sine x equals 0. Then now next one is tangent x. So the second equation involves tangent. So we're going to solve this one now. So if tangent x minus square root of 3 is 0, then that means tangent x is the square root of 3. So what is x? X, if we do the tangent inverse, right, this one will return a value that is a value from only negative half of pi to positive half of pi. That means an x in that. Could you think of that angle x whose tangent is the square root of 3? Pi over 3. Yeah, so if that's a special, yeah, pi over 3, right? So that is the the x whose tangent is square root of 3. So now, but that is an acute angle in this range. However, can we still have another, but we know the tangent possibly pi over 3 because tangent is periodic, right? If you add another pi, you will get the same tangent value. So for example, tangent at this is still square root of 3. So you add a pi. Let's see. That is what? Pi over 3 plus pi, we get 4 pi over 3. Yeah, 4 pi over 3. You see, that is still in this interval. Yeah, so but if you add another pi, it's going to go beyond that interval. So we have two solutions. One is the pi over 3. Using tangent inverse, we can find immediately, we find 1. But the other one is 4 pi over 3. Both solutions are in this interval. So let's summarize. How many solutions? So we have 0 and pi. And then we have pi over 3, 4 pi over 3. So the whole process is that to answer the part A, we actually, by factoring, we solve two equations, right? One equation involves sine x. The other equation involves tangent x. By solving each equation, then we can find all solutions over this interval from 0 to 2 pi. So now we can list all solutions. We can list all solutions. So we have a total of 4 solutions, 0, pi over 3, 4 pi over 3. Now, suppose we want to solve the equation to find all solutions over this interval. So recall that we have 0 and pi, right? For this to be 0. And then we have pi over 3 and 4 pi over 3 for this one to be 0. So we found 4 solutions on the interval from 0 to 2 pi. Those are the answers for part A. Now we want to answer the part B. In order to answer the part B, let's list all solutions over the interval from negative infinity to positive infinity. So all solutions, think if you have found 0, that's one solution, but n integer multiple of 2 pi can be added to 0, right? That is still a solution. So that means we can find many solutions from one solution. So then pi, you can also add n integer multiple of 2 pi to pi. Because the sine function has a period 2 pi, that means n integer multiple of 2 pi can be added to the solution and still produce the same sine value. So then we can find so many more. So this one, let's rewrite it so you can see. This is simply 2 times n times pi, right? This one is 2n times pi. Add another pi, you see, there's plus another pi. So this is actually 2n. If I factor out a pi, so it's 2n plus 1. So we notice that this is an even integer. a multiple of pi. This is an odd integer multiples of pi. So even together with odd, and basically it can be written as just the integer multiple of pi, because this together, the two cases, means I can simply write it as k times pi. K is the integer. It can be either even or odd. So we can write our solution, you see, from either this one or that one. We can write it as k pi, where k is an integer, right? K is an integer, an integer. Okay, so if k is any integer, that means it can be even or odd integers. So we combine this whole set of solutions, that's another set of solutions, into a short form. That is a very clean way to write, to combine this set on the other side. So, okay, we have k pi, k times pi, k as an integer. And then, so with this tool written as k pi, then I can, I'm done with this part. So we have found all solutions, right, for this sine x equals 0. Then we continue to move on to those values, pi over 3. So if pi over 3 is a solution, if pi over 3 is a solution for the second equation, the tangent x, remember this second equation is just the same as if you write it this way, tangent x is square root of 3, right? That's the equation we're solving. So for this equation, you can find x is pi over 3. So suppose you find 1, then you can find more. That is, any integer multiple of pi can be added, because tangent has a period pi, tangent function. Its period is pi. So any integer multiple of pi added to the pi over 3, still that will be another solution for the same equation. So we have many solutions here. K is again integer, right? K is a integer, can be 0, positive or negative integers. And how about one more? 4 pi over 3. 4 pi over 3. Again, because we're solving this equation involving tangent. So tangent function has the period pi. So if you add any integer multiple of pi, and this is the set of possible values of x, whose tangent is still the square root of 3, right, for this equation. So k can be any integer, and see, you can find all these are solutions of this problem over the interval from negative infinity to positive infinity. And also this part will be solutions for the sine x equals 0 over this interval. So together, how many solutions? K pi. And that is the solution to make this part 0. And then pi over 3. So recall that if we look at the tangent the other equation, tangent x equals square root of 3. And recall that we have pi over 3, right? Either this one plus a multiple of pi or this one plus a multiple of pi. And this 4 pi over 3 can be rewritten. The way we see this 4 pi over 3, let's keep this in mind. This is pi over 3 plus a multiple of pi, or 4 pi over 3 plus multiple of pi, in order to make this one true. So this is a tangent x equals square root of 3. We're tackling this part. So the x can be this or this. But the 4 pi over 3 can be written as pi over 3. We split 4 pi over 3 into two parts, you see? 4 pi over 3. And then it's pi over 3 plus pi. And then keep the remaining part, which is an integer multiple of pi, still there. Yeah. So what is happening is that we can group this, because that pi, after you factor out the pi, you see n plus 1. So pi over 3 plus n plus this integer multiple of pi. So that means the sides are the same, essentially the same, because this n is arbitrary, so n plus 1 is also all the possible integer values. So if you rewrite this set of possible solutions, this is the set of all possible solutions. They are essentially the same set, only because the second one can be written as, you see, pi over 3 plus some integer multiple of pi. So after we compare, this one is essentially the same, right? We can write as, so we just write it once. You don't have to repeat the same set. Although they look different, they are essentially the same set of values. So we just write this once. So pi over 3 plus an integer multiple of pi, k pi. So I just changed the name. So this n or n plus 1 is just an integer. Let's call it k pi. So it doesn't matter if you choose still n pi. That doesn't matter. It's the same, right? So it's just for you to see that we can, the two sets is essentially the same set. So now we just write pi over 3 plus k pi for tangent x to be square root of 3. And this k pi is for sine x to be 0. So now let's see that quick summary for this problem. So for this problem, after factoring, we can find we can factor, and then quickly we can solve for the sine x and tangent x. Once we get sine x and tangent x, then we can solve each equation, right, over the interval. That's the part A. Once we get the solution over that interval from 0 to 2 pi, then you can easily find all solutions on the entire real number line, all possible solutions. So for the sine, for the equation involving sine function, you should use the fact that the period of sine or cosine is 2 pi. For the tangent, if you find a solution, then all you need is to use the fact that the period is pi for tangent. So for example, if we find one solution already using the tangent inverse, we find that, right, using tangent inverse, we can find x, which is pi over 3. Yeah, if you can find this one, then you can find all, because pi over 3 plus any integer of pi will be still solution of this equation over the larger interval. Yeah. So that means this is already possible for the tangent function. As soon as you find one solution, then use the period of tangent being pi, then you can find all solutions of this equation over negative infinity to infinity. That's why it's not surprising that when we try to find all solutions, then we get this part and that part. Yeah, you do the color coded, because this one is for tangent x, right, to be square root of 3, and the blue one is for sine x to be 0. So you see but together they are all possible solutions for the trigonometric equation.